summary of the Melamchi Water Supply Intake and the methods that we used to assess risks at the intake and to design a system that is less vulnerable to the debris flood hazards that exist there. So I assume that most of you in the room know quite a lot about the Melamchi project. Is that true? Like by a show of hands, you're very familiar with it? Yeah, okay, many of you are, I assume. My understanding of the project is very specific. Right? I learned of the Melamchi project about 2 years ago, after the debris flood occurred that buried the water supply intake. And I was part of a team that was asked to assess the hazards and to develop a plan for managing the risks. And so what I'll be sharing is my narrow view on that specific question, which is how to manage the risks specifically to the water supply intake. Okay? So I'll provide a project introduction. I know for many of you, you probably know the introduction, but for some of you in the room, you might not. Then I will describe the risks and the risk reduction options that we considered. And last, I'll walk through the risk management design. And all of the concepts and all of the tools that we use to make decisions for Melamchi have already been presented to you. So hopefully this is an illustration of how we have applied these tools in practice. So maybe a better question is, please raise your hand if you're not familiar with this project. Is there anybody who's not familiar with it? A few hands? It's okay. Okay, good. So here we are in the Kathmandu Valley. Here. And we have the Indrawati River that flows past the valley. And at about the same elevation as Kathmandu, one of the rivers in the upper portion of the larger Indrawati is the Melamchi River. There's a tunnel that connects Kathmandu to this river at about the same elevation, and the water from the Melamchi River is diverted through that tunnel to Kathmandu. At the very upstream end of the tunnel, we have the structure called the headworks, or the intake to the tunnel. So we take this water that's here, this very muddy looking water, and it flows in, so this is upstream here, it flows into the headworks and the intake, which is, you can't see it, it's on the other side of this road. The water flows in here, and the sediment and the gravel and the sand are separated from that water. All of that sediment is flushed out below the weir, and the clean water continues beneath your feet to Kathmandu. That's how the system works. This project was finished. They built the tunnel, they built the water treatment plant in Kathmandu area, and they had finished the headworks. And within, you know better than me, within weeks of when the project was completed and when the headworks was completed, there was a debris flood that buried the intake. So this yellow thing here is the same as the yellow here. This is the same. So you can see that the sediment built up and entirely buried the structure. This is what it looked like during the event, early in the event, before the sediment actually ended up filling all of that. This is early in the event. This is the debris flood that occurred. And of course that affected the water treatment or the water intake, but it also affected the communities downstream in even a much bigger way, filling the communities along the riverbanks with sediment. This is the community of Melamchi Bazaar. Dozens of people lost their lives. Hundreds of families lost their homes and their businesses. This is what the community looked like near Melamchi Bazaar about a year after the event. So you can see that the sediment filled the lower level of the... So these buildings are no longer inhabitable. And the river, which used to be here in the channel next and this side of the building, is now 5 times wider than it used to be because of the deposition that occurred. So we had, this event was, we call it a debris flood because it's the debris flood that impacted the community downstream. It had a combination of triggers. It had heavy rainfall and early warm temperatures in the high elevations, and that created a glacial lake outburst flood. There's some debate about whether there was also a landslide dam outburst flood. But the key point is when you had this debris flood, you had these direct consequences. 25 people killed, 6 injured, over 300 fully damaged homes, 500 displaced families, 20 bridges destroyed. Indirectly, there's also a loss of the water supply to Kathmandu for some period until the intake could be reinstated. And then there's the related loss, or unrelated, but in the Melamchi Bazaar you have things like lost business revenue, increased travel time and cost due to the damage to the roads, and the intangible consequence of community trauma. So BGC's role, and this was the project that I was involved in, I was hired by the Asian Development Bank along with my colleagues to design protection for the intake from a large landslide. So the intake is here. You can kind of see these little yellow dot and a black dot there. That's where the intake is located. The water used to flow into the intake here, and the sediment was taken out and flushed back to the river here. And there's this large landslide above it that was triggered by the debris flood. And then there's also the debris flood itself. So we were hired to manage the hazard specifically being this process of debris floods and landslides. So we were asked to stabilize the landslide and to stabilize the watershed to prevent the debris floods. That's how our work began. So now beginning with the landslide, this landslide is about 1/2 kilometer across, 1/2 kilometer high or so, and it's something like 40 meters thick. It's on a very steep slope. Right, so the intake is way down here. We have this large landslide. It's sliding along the foliation plains in the metamorphic bedrock. You have risk to the communities above, but our scope was very specific to the intake, which is there below the landslide. And you can see that this landslide is very large, and it's inaccessible. I mean, you can drive to the top, but there's no reasonable way to build roads onto the landslide to stabilize it. Because if you build a road to the landslide, that road becomes a conduit for water. And so we were afraid if we built roads, it would make the situation worse by introducing more water to the landslide. So that's a summary of the landslide that we were asked to stabilize. We were also asked to stabilize the sediment sources that contributed to the debris floods, because the intent was to prevent the future debris floods from occurring. I mentioned that there was a glacial lake outburst flood that was up here around the corner. That glacial lake outburst flood came around the corner and it deposited this sediment here. There's this flat plain. There's this flat plain here that's created by an ancient landslide dam. So across here is an ancient landslide dam. And behind it, over a period of centuries, the landslide dam filled in with sediment, with silt and fine sand. It created a plain called Bemetan. And during the glacial lake outburst flood, much of the sediment from the flood that was upstream was deposited on this plain, but the water cut into the ancient landslide dam and created what we call a nick point, which is an area of erosion. This is that nick point. It's about 130 meters high. And here is a video. We're flying, not we, sorry. I've taken this from Babu Lama's Facebook page. So Babu Lama is flying in this helicopter, taking a video. He is flying across this Bemetan plain, and we're about to reach what I'm calling the nick point. So this is the point of concentrated erosion, where the sediment that is contributing to the debris flood is coming from. So here's the sense of scale. You can see that we have sediment falling in from the unstable slopes on the side, constantly. And then here's the big nick point. And here's all of the erosion that has happened because the bed level has cut downwards. That's destabilized the slopes, so now we have sediment coming in from the sides. So the helicopter has turned around, it's now flying back up the channel, just showing you the scale of the sediment hazard, the sediment sources. On this plain, the Bimathon plain, at the downstream end, there's 8 meters of sediment that was deposited from the glacial lake outburst flood. At the upstream end, it's much higher than 8 meters. So there's a large volume of sediment from the outburst flood that didn't continue downstream. It actually deposited. But the debris that came downstream was mostly from that erosion of that nick point in the video that I showed. So that sediment was carried for many kilometers downstream. I don't remember the number, but maybe this is 10 or so kilometers downstream at the headworks. And almost everywhere, from the headworks up to that erosional feature that I showed in the video, it was all erosion. Almost no deposition in those areas. The river was cutting down and taking sediment from the banks. And right where the intake started is where the river gradient changes a bit. The river widens a bit. And so we had here a deposition of about 20 to 25 meters of sediment. And that deposition continued for 50 or more kilometers downstream. So a thick layer of sediment deposited in the channel. This is a photograph from about a year afterwards at the intake. So the sediment level was up here, but the subsequent monsoon eroded into the deposit and carried some of the sediment downstream and started to expose parts of the intake. But even here, the weir and the small dam is still buried under something like 8 meters of sediment. And so there's no way to flush the sediment. So if you were to take water in here and continue to Kathmandu, there's no way to take the sand and the gravel out of the water because it's not possible to flush it back into the river because those flushing valves and pipes are many meters below the surface. So that's the problem. Are there any questions about the problem before I continue? Okay. So now we'll talk through the risk management framework. This is an example of a site-specific risk management. So we're not talking about prioritization. We're just talking about we have a problem that we're trying to solve at this specific place, and our goal was to find the most cost-effective, fair, affordable, reasonable way to manage the risk. So I'll first talk about identifying the risks and then identifying the risk reduction options. So there was initially pressure for us to focus on the hazards. So we were intended to characterize the landslide and characterize the debris floods and stabilize the hazard. Basically, our job initially was to keep this big boulder from falling down on the house, right? But we knew from our past experience that a better approach would be to start at the element of risk and to work our way up to the hazard so that we didn't waste time focusing on something that really isn't helpful for solving the problem. So we started by focusing on the intake, and I'll show you how we did that. So we started the risk management design by identifying the elements at risk and the consequences that we wanted to avoid, and we were very specific with how we defined those consequences. So maybe a quick discussion amongst your group. What are the consequences of debris floods and landslides at the Melamchi River? See if you can make with your group a list of, say, 5 things, 5 different types of consequences. I'm just trying to make the point that there are many different consequences and you're going to approach risk management for those different consequences in different ways. So talk amongst your group quickly. Already raise your hand or somebody call out what is a different type of consequence? Specifically, yes.
to the headworks.
Structural damage specifically to the headworks.
Starting from the headwork.
Yes.
Then after the workers that are working in the headworks, that's the loss of life. And also coming towards the downstream, we also had the damage in the local people residing at the downstream.
Yes.
And also the businesses that were running right
yes.
beside the Melamchi River.
Yes.
That was economical damage. That's it.
Yeah, excellent. That's excellent. That's exactly what I was hoping. That I want to make is that you manage the risks for those consequences differently, right? So you're going to manage the safety risks to people potentially differently than you manage the structural risks to the intake. So I'm going to talk today mostly very specifically about the structural risks to the intake. So first, we'll talk about risk number 1, which is the water supply intake being buried by a landslide. This is the consequence that we're trying to avoid. So this is the risk that we're trying to manage. So we have our intake, and then we have our landslide. So we started by thinking about what are the things that are creating the risk. So for the landslide hazard, when we try to be specific, what it is it's not just that there's a landslide. We need to understand more about the landslide, right? We need to understand more about the process. We need to understand the size or intensity of it and the frequency of movement or the likelihood. So in this case, we have a rapid, the concern is, or the hazard, is that we have a rapid collapse. So we have a large landslide that collapses suddenly, buries the intake. And this thing is so large, the size of it is so large that it buries the intake under 50 meters of sediment or more. And that deposit is made of large boulders, 50 meters in diameter or more, that really can't be excavated and removed easily. So we have a complete picture. It's not just a landslide, but it's something more specific. Our exposure, again being specific, is that we have an intake that only has one entrance. There's one entrance, and that's the only way for water to enter the tunnel. And that intake is below the landslide, directly below it. And what makes that entrance vulnerable is that it's only about 4 meters high, and the landslide deposit is going to be much more than 30 meters thick. And it's also not designed to be impacted by the landslide. Right? So that's what makes it so that we could have this intake buried by the landslide. So our risk reduction options for the landslide, number 1, we could stabilize the landslide. Number 2, we could move the intake to a location that's not affected by the landslide. Right? That would be reducing the exposure. Does that make sense? Yeah? We could also reduce the vulnerability. So we could design an intake that is resilient so that if the landslide happens, it doesn't bury it. Maybe it's a very tall intake, or maybe it's very strong, made of reinforced concrete so that it can withstand the impact pressures. Those are options. I'm not trying to say that these options are feasible or a good idea. We're just listing, kind of brainstorming. This is what we can consider as we move forward through the process of making a decision. Is that clear? Yeah? So I'm not suggesting that this is a good idea, just that it's a possible idea. I'm going to move past this because I think we're short on time, but I'm trying to make the point that the intake buried by a landslide is different than the intake being buried by a debris flood. You have to manage those risks differently. They're different consequences. They're different hazards. And so it may not be possible to manage both of these issues with the same risk management plan. So we looked at them separately. Yeah? So I'll go through this quickly.
Alex?
Yeah. Okay. So for the debris flood, I'll skip to the risk reduction options. So an hour and a half would get me till 4 potentially. Okay, I'll try to aim before. Yeah, okay. So the options for the debris flood, managing risks, risk reduction options for the debris flood are we could stabilize, if we're going to talk about the hazard, we could try to stabilize that very large nick point. So remember the helicopter video, you could see the large slopes of sediment raining down. One option would be to stabilize that. Maybe not a good option, but it's an option. You could also, if you believe that that was triggered by glacial lake outburst floods, you could try to manage the water levels in those lakes to reduce the potential for those floods. On the exposure side, you could move the intake to a different location where you don't expect there to be deposition, right? Because the main issue was we have a deposit of sediment. So if you move it to a location that's very narrow, then you have the sediment moving through without burying the intake. So now we're not exposed to burial by the debris flood, right? We're still exposed to the debris flood, but we're not exposed to the debris flood burying our structure under many tens of meters of sediment. And then the vulnerability, we could develop an intake design that still allows the water to enter even if the intake starts to bury it. That's an option. So this third risk, I'm not actually going to talk much about it, but I want to use this as an example, like an exercise for the groups. Okay, so I talked about two different risks that we were trying to manage for the intake, but as a group, let's talk about options for managed risk to the people who are living downstream. Okay, so let's work on that in your groups. We'll begin with, again, the risk is people killed by debris floods, and maybe I should add, who are living downstream in the communities. So work with your tables. I'll give you a couple of minutes, maybe like 5 minutes, to draw the diagram or make a list in 3 different categories of what are the hazard, exposure, and vulnerability components that create the risk. Okay? Go ahead, please. This is the risk that we're dealing with. It's the risk of
post-disaster epidemics.
Post-disaster epidemics could be a separate. Yeah, it's a separate issue. Yeah, so you could have the debris flood that damages services or creates other issues that then leads to an epidemic. Is that what you're describing? Like a health issue. Yeah? Okay. All right, let's talk about the exposure. So what is the exposure? We're speaking of this risk. We have to go to a different table. I know you have ideas. Next table. What is the exposure? It is something that's exposed. But if we're talking about a risk of people killed by the debris floods, then I would describe it as, people who are on the... So the person using the infrastructure would be the thing that's exposed in this case. Okay? People who are walking in the downstream area. Working, yeah. That's right, that's a good point. So you could have workers, and I know the Chamoli incident, there was many workers who were killed from the debris flood there. Yeah, so workers would be a different type of exposure than, say, somebody who's living in a building, because you would manage the risks differently. Yeah, so you need to consider them as different types of exposure, yeah? Good point. All right, what about vulnerability? How about this table here? What do you have for vulnerability? Things that we're trying to avoid, but if you have a debris flood that impacts, say, a worker, what is it that makes that worker vulnerable? So I would describe it as the reason that the people could be killed, the reason a worker could be killed, the reason they're vulnerable, is because they're in a location, usually that's a confined space where they're working, and they're not able to escape. That's why they're vulnerable. The reason they're killed is because they can't leave. Yeah? Maybe a person living in a building, the reason that they are vulnerable is because they didn't hear it coming. They didn't know it was coming, so they couldn't leave. right? That's what makes the person vulnerable who's in the building.
The boulder also.
Sorry?
The big stones and boulders.
Yeah, the boulders, I would say, are part of the hazard, and the people are vulnerable to it because it's really big, and if it hits a person, it will kill the person. Yeah? Okay, so here's how I filled it out. The hazard that we were interested in is debris floods in the Melamchi River, and I agree, things like bank cutting and subsequent landslides, you could add that as contributing hazards as well, I agree. The exposure, I had people who are living, sleeping, working in a debris flood zone, people who are in buildings. And then what makes those people vulnerable is the idea that the people who are not able to evacuate are the people who will be killed. The people who are able to evacuate are not as vulnerable because they can get away. Another thing that makes this vulnerable is that the sediment fills the lower portion of buildings, so it makes it so people are not able to escape. And then another thing that creates vulnerability is if there are buildings that collapse, as you described for the bank cutting. So if the bank erosion happens and the building collapses into the flow, that contributes to people who are being killed. That's what makes the people vulnerable to death. Now, what are the risk reduction options? Right? So use the same diagram you can write for hazard. How can you reduce the hazard? How can you reduce the exposure? How can you reduce the vulnerability? Again, we're trying to be very specific to this risk. How can you manage this risk of people killed by debris flood? Reducing the hazard, the debris flood hazard. What idea do you have? No? What about the other back corner? Okay.
Diversion from the community area to reduce the flow that's coming in that area. Geotechnical investigations and retaining structures. River draining structures. Yeah,
okay. So I'll focus on the river training structures and diversion structures. So that's right. You can reduce the probability that the hazard impacts with structures that control where the hazard goes. Yeah. What are other ideas for reducing hazard of debris flood? Are there any?
Vegetation and land management.
Vegetation? Land management. So trying to stabilize the sediments in the watershed so that it's not available for the debris flood. Yeah. Okay. Good. What about exposure? What about this table here? What do you have for exposure? How do you reduce the exposure? That's right. You can move the people who are exposed or the settlement to a new location. Yeah? Okay, so you could have bank protection so that the river doesn't move into the development. Yeah? Awareness of the hazard. Okay? So people are able to leave. Yeah, okay. What about vulnerability? What do we have for managing vulnerability? Maybe this table back here.
Strengthening buildings.
Strengthening buildings, yes. Yeah, you could retrofit structures so that if they're impacted or if they're eroded, they don't fall or collapse. What else?
Insurance coverage.
Insurance coverage, yep. You can reduce economic damages that way.
People diversification.
Okay. All right, so let's see what I put for reducing the hazard. And again, this is not an exhaustive list. So many of the things that you've listed would be additional, but the things I listed quickly are you could stabilize the debris source in the watershed, or you could try to manage the water levels in the glacial lakes. This would reduce the hazard. To reduce the exposure, you could use land use planning to minimize the population living in the hazard zones. This would be identifying locations that where you encourage development and other locations that were within the hazard zone that you would discourage development. You could have a warning and evacuation system so that people evacuate from the hazard zone during floods. That would be reducing their exposure. And then you could also identify safe evacuation sites that are outside of the impact area. That would reduce the exposure of people to the hazards. Now, to reduce the vulnerability of the people, you could have public education and training so that they are able to recognize the hazard and they know where to evacuate to. You could also have local building protection, a thing that's hard to control, so there aren't that many options often. And this is why we start at the downstream. We look at the element that's going to be impacted, and we think about how do we manage the exposure, how do we manage the vulnerability, just as we heard from Inset yesterday, right? We heard from Ramesh about how do you manage the landslide risk, or sorry, the earthquake risk. You can't stop the earthquake. There's not much point in trying to stop the earthquake. So you focus on the buildings. Yeah? And we're trying to do the same thing when we do a debris flood or landslide risk management project. Are there any questions or comments before I move to the next section on the risk management design process that we follow? No? Okay. So now we had that long list I showed you 2 slides ago. We had all of these ideas for how we can manage risk to the intakes, but then how do you decide? Right? We understood the risk, but now how do we decide which of these to implement? And that's what I'll talk about now. Oh, that's what this slide says. Okay, we have the ideas, but what should we do about the risks? So often, it helps to take a large problem and break it into smaller pieces, and that's what we did. So we decided that there were initially 4 decisions that we had to make. The first decision was, is it feasible to prevent or reduce debris floods? Because we recognized that if you prevent the debris flood, then it solves all the problems. So of course, if we can do that, that's the best case. The second decision was, is it feasible to stabilize the landslide? It's the same issue. If we could stabilize the landslide, it solves all the problems. That would be ideal. The third decision was, should the intake be relocated? And the fourth was, what is the most reliable layout of the intake? So again, the initial problem that was brought to us was, how do we manage risk from debris floods and landslides? And we decided that problem is too big to solve. We can't solve it like that. We have to break it into individual decisions that we can work through one by one. As I said, if we could reduce the hazards, if we could reduce the debris floods and landslides, we would be able to manage all of the risk downstream. So clearly that was the best place to start. So I'll talk now about, is it feasible to prevent or reduce the debris flood hazard? I could spend all day speaking about the more detailed assessment that we followed to answer this question. But given the constraint on time, I'll just quickly run through the types, like the steps of the analysis that we did to reach the decision. Okay, so that's what this is. So the first step that we followed was to assess the cause of the previous debris flood. We needed to understand what caused it, because that helps you understand what could happen in the future. And what we learned was, it's not really important what exactly the trigger was, right? There could have been debris flood that's caused by any number of glacial lakes in the watershed. There's many of them. And really it doesn't matter which lake it starts from. The important part was that there is this bimathon deposit that has a large nick point. And that means that no matter why there is heavy water, whether that's heavy rainfall or glacial lake outburst flood or landslide dam, the fact is you will have a debris flood because there's that very large source of sediment. And so that's what we determined was the cause of the debris flood. It was that large source of sediment. And some of these other details are less important. So that led us to step 2, which was to assess the likely causes of future debris floods. So the question was, the first debris flood was caused by that big erosional scarp in the bimathon deposit. And we wanted to know, is that going to be the cause of future debris floods? And we said, certainly yes. Right? We have this huge deposit of sediment sitting there. Every time it is heavy water flow, we'll have debris floods. Next, we tried to identify all of the sediment sources. And what we found was that the sediment source is almost infinite. It's so large, over so many kilometers and so high, that it doesn't really make much sense to try to quantify it. It's infinite for all practical purposes. The next step was to estimate the size of future debris floods. And the way that we did that was to begin by estimating the size of the previous debris flood, the one that happened in 2021. So we estimated with some uncertainty what was, the minimum size that it could have been and what was the maximum size. And because the sediment source in the future is the same as it is now, we could say, well, the future debris floods will probably be, with some uncertainty, in a similar range of size as the previous. Next, we identified the options for reducing the frequency of the debris floods, because remember, the question here is how can we reduce the debris flood hazard? Debris flood hazards have two components, right? The frequency or probability or likelihood, and also the size. So we looked at those independently. How could we reduce the frequency? Well, we couldn't think of anything. There's no way to reduce the frequency, right? Because the frequency is related to the rainfall, it's related to things about the hydrology that we can't control. And we can't control the sediment source because it's too big. After we thought about frequency, we said, well, are there options to reduce the size of the debris floods? In a typical watershed where I live, one way we could reduce the size of the debris floods is to try to manage the sediment. So there was the idea of trying to vegetate the slopes to reduce the volume of sediment. But at this site, it was clearly impossible to do that. The scale is too large and the location is too inaccessible. So we saw that it's not possible to reduce the size. And so the last step was to decide, are any of these options feasible? And we decided no. No, it's not feasible to prevent or significantly reduce debris floods. There were some ideas about building gabion check dams in this channel to try to stabilize the channel. And we felt quite strongly that that would not be effective. The gabion check dams are just simply not strong enough. So there was sort of a pressure to go and show that something was being done to manage the hazard. And there was pressure, let's go and do that because we'll show that we're doing something productive. And we recommended that no, that's not productive. It may sound productive to people, but all that's going to happen is you're going to waste money building those check dams. And the first event that you have, it's going to erode. And so I guess I want to encourage you that when you know that's the case, to step up and say, no, this isn't a good idea. This is not a waste. This is a waste of funding and effort. And that's an important decision. So the next decision was, is it feasible to stabilize the headworks landslide? So the headworks is down in this area at the bottom. This is the landslide here. A good question was asked at one of the breaks, not the breaks, but one of the group exercise times, about when did this landslide happen? Well, the landslide was an ancient landslide. It had been there for a long time. And during the debris flood eroded the toe of the slope, and that caused the landslide to remobilize. So during the event, all of this lower portion of the landslide slid down the hill, and this material in the trees here, you can see, it slid partially down the hill, but not all the way. And that was the problem. If everything had come down at once, then there really wouldn't be a landslide hazard still remaining. But the problem was only about half of it came down, and the half that came down destabilized the pieces above. So now we have the hazard from the pieces that are still hanging on the slope. And this landslide is sliding on foliation planes in the metamorphic bedrock that were dipping parallel to the slope. So the steps that we took to assess the landslide hazard, or to assess whether we could stabilize the landslide, were first, we mapped the landslide extents. Secondly, we recommended this, and we started this, but it didn't happen. But I want you to be aware of what we would like to do, which is, when you map the landslide extent, that shows you the area of it. But you also, in order to stabilize a landslide, or design the stabilization, you need to understand the depth of the landslide. Geophysics was done to investigate the depth, but really geophysics is not very certain. When you do geophysics over a landslide, you really don't have a good idea of exactly where the movement is. So the best way to understand that is you drill a borehole, and within that borehole you install an instrument. One is called a slope inclinometer, and it's basically a pipe that goes into the ground. And when the landslide moves, let's say it moves here, the pipe at this location deforms. So now instead of the pipe being straight, the pipe goes down here and it has a bend and then it goes down. And so you can measure the depth to that movement. And if you do this measurement, say once a week or once a month, you can estimate then the amount of movement per time. That gives you a displacement rate. There's also now automatic versions of that where you don't have to return in person, but it's a digital system that measures those deformations and can send an alarm or send you the information through satellites or through a telemetry system that could be through satellite or cellular or other ways. The other thing that we recommended but didn't actually happen was what we call LiDAR change detection. So this is probably the least expensive and most effective way to quickly understand a landslide. It's actually quite easy, and it's quite possible to do these days with drone technology. So you can have a drone that flies. This is a relatively small area. It's about 0.5 kilometer by 0.5 kilometer. The drone collects a digital elevation model using LiDAR. Then you come back sometime later with the same drone. You collect another digital elevation model, and you overlay one over the next. And you have a model that looks like this. So this is a LiDAR change detection at a landslide in Canada. The colors are showing you relative change. So the blue is showing depression or moving downwards of the landslide. The red is showing bulging outwards. So if you do the LiDAR change detection, you do a couple flights of the drone, you can use relatively simple software to then see what is the area that's moving, what is the rate of movement, and then I can tell you quite a lot about the mechanism of the landslide and the likelihood of it collapsing. Because remember, likelihood is a key component of understanding the hazard. So after we recommended LiDAR change detection, the next piece was to assess the failure mechanism. So this is just us trying to understand the landslide, basically what is the thickness, what is the size aerially, and how quickly is it moving, and what is causing it. In this case, the cause was the foliation plants. The next step was to assess the potential for rapid failure. Because remember, in our case, what we were really concerned with is the landslide collapsing all at once and burying the landslide. So if the landslide comes very slowly, piece by piece, the river just erodes it away, it's really not a problem. So we needed to know, could it collapse all at once? And we decided that yes, it could. It could collapse all at once. So once we understand this potential, the next step is to identify stabilization options. So how can we stabilize the landslide? There's basically, well, there's a few options. One, you could remove portions of the landslide by excavating it. We decided that's not possible. There's no way, there's no place to move the material in any way. It's way too expensive. Secondly, you could try to buttress the landslide. You could build something at the bottom to try to hold it in place. And that wasn't possible because the river would erode all of that material. So there's no way to build a buttress at the toe. The next idea was to try to remove the water from the landslide. And we decided that wasn't possible because you couldn't access it easily. And there wasn't, with this type of landslide, there wasn't a clear way to drain it effectively. And then lastly, you could try to install anchors into the landslide to stabilize it. And again, the landslide was something like 40 meters thick, so it just wasn't possible to install anchors to that depth at the spacing that would be needed to stabilize it. So we learned that it wasn't possible to stabilize, so therefore there were no feasible options.
I think even more than 40 meters.
Yeah, more than 40. That's a good point.
We did the 3 drillings.
Yes.
On the top, middle, and toe, and then we didn't get the core rock until 60 meters or 65 meters.
Yeah, that's a good point.
And then we stopped drilling.
Yeah. So that's a good point. So we did some geophysical surveys at the beginning that suggested the thickness was something like 40 meters. But as we drilled holes into the landslide to learn more, we saw that it was actually deeper than that. So it wasn't possible to stabilize just because of the size. So remember, the ability to reduce the hazard depends on the size of the hazard. And in this case, the size was simply too big. It's very thick. It's very, very large volume. And the material looks like this. The landslide is broken up, so there's no way to install anchors into that. So the decision was no, it's not feasible to stabilize the landslide hazard. So that meant that these options for managing hazard were all gone. There's nothing that we can do to manage the hazard. So what's left? How do we manage risk then? Yeah, we have to reduce the exposure and the vulnerability. There's no point in thinking about the hazard more because we cannot solve the hazard. And I know we said there's lots of key messages, but maybe this is the one I really want you to remember. Know the purpose? Yeah, Emily says know the purpose. But what I want to say is that you cannot always reduce the hazard. And when you can't, that's okay. We have other options. We can reduce the hazard, the vulnerability of the exposure. So again, we said we would break this big question into smaller decisions. Once we decided that we can't reduce the hazard, we had to decide, well, should the intake stay at the current location or should it move upstream? There's 4 locations that we looked at. One was leaving it at the current location. Next was to move it about half a kilometer upstream to this very narrow section. The advantage of the narrow section is that there's almost no deposition of sediment there because it's very narrow, so there's always erosion, and it's all bedrock all the way around. And then the next option was Sakatali. It's about 1 kilometer away, and that's where the river starts to widen. It has some sedimentation, but not nearly as much as the current site. And then Nakote, which is about 4 kilometers away, which is also a narrow gorge similar to this one. So the first step of this was we wanted to define the problem and the objectives very carefully. So the simple decision was, should the intake be relocated? But how do we solve this question? Well, the first step is to help make a very detailed problem statement because that'll help us solve it. So we took this simple thing and we said, well, the real decision we want to make is, will the risk reduction achieved by relocating the intake, so the amount of risk that's reduced by moving it, will that be worth the additional cost, time, and environmental footprint needed to relocate the intake? Right, so we recognize that nobody wants to relocate the intake. Nobody wants to do that, right? It costs more, it has a larger footprint, it's going to take time. But our question was, is it worth that? Right? Is the risk so high at the current location that it's worth those additional costs? That was the problem we needed to solve. So now I'll talk about the decision tools that we used to make that decision. So the first part of that decision was, okay, if you're going to move the intake, where do you move the intake to? Right? If the whole point in this case is to avoid the large landslide, we needed to know where are the large landslides and where is a safe place that avoids them. So one thing we recognized is we mapped all of the landslides that existed along the river. And those are outlined here in yellow. There's one here, there's one here, there's one here. Because we had to characterize the landslide, we knew that the mechanism for sliding was what we call planar sliding. So the geology in the area is we have foliation. Raise your hand if you're not sure what I mean by foliation. It's okay. If you don't understand, or now I'll explain it. Yeah, okay. So foliation. So you know that there's different types of rock, right? You can have a sandstone that's all sand. You can have shale, other things. The type of rock here was what we call a gneiss. And a gneiss rock is a metamorphic rock that's created when mountains are built. So when mountains come together, there's a lot of pressure that pushes on the rock, and the rock is heated and it's under a lot of pressure. And as that happens, the minerals within the rock kind of reorganize themselves.
Something like that.
Yeah.
Slides.
Yeah.
Structures are here. If the orientation of the foliation is towards these structures, it can slide easily. So these are the...
Exactly, yeah. So what we're saying here is the minerals reorganize on these planes, and we have this sliding down on those minerals. And this is like this over the whole region. Everywhere is like this. It's all going in the same direction. So the problem is, if you have a river that cuts through this way, like there's a river this way, you see that it's not going to slide. But when the river cuts through this way, what happens? You have to let it slide. Good, let it slide for like dramatic effect. Right, that's your important iPad or something, right? No, just okay, so yeah. Thank you, catch up. You notice that the river, whenever we have a landslide, the river is in the same orientation. That's because the river is cutting at the base of those plains and causing the landslide to slide above. So because we understood the landslide mechanism, then we could identify locations that were not prone to that mechanism, and that's anywhere the river is at a different orientation, right? So here, the river is perpendicular, so we said, that's a safe place that doesn't have a large landslide. And here as well, right? It's at a different orientation, so we don't have the large landslides. So once we understood that, we picked these 4 locations to avoid the landslides. Now we needed to compare the different locations. And we started by comparing the risks. So what we decided for the existing intake, we thought that the probability, we used a simple, we call a risk matrix to do this. So for this site, we decided, well, the probability of that large landslide coming and burying the intake was something like 1 to 10% per year. We're not certain that the landslide will come down. We don't know. But we know that it's moving. We know that it's very large. We know that if you have another heavy rainfall event, it could all come down as it did last time. So we said, well, it's not very certain, but it's also not very unlikely. It's sort of in the middle somewhere. But we know that at the existing location, if the landslide occurs, it will completely destroy the intake. So we have a complete loss. So using this matrix, we call this high risk. Does that make sense? Yeah? Then we looked at the next site, another site. We looked at all 4, but I'm just going to compare the 2 to help with my discussion here. So this next site we looked at, Sarkatali, site C. At this site, we don't have large landslides, but what we do have is debris flows and debris floods. And we know that those debris flows and debris floods come quite often, especially from, so we have the debris flows and debris floods in the main channel, but you also have them from the side channel. So we wanted everyone to understand that this site is not perfectly safe from the hazards. There are always hazards here. The difference is, although the hazard has about the same probability as the initial site, the main difference is that if a debris flow occurs here, it's something that you can recover from. Right? There's only a short disruption. The debris flow buries another 2 meters of sediment. Oh, you can clean it up and start again. So it doesn't cause a complete loss, so it plots here. So this site is low risk. Right? Sarkatali is low risk. The existing intake was high risk. But remember what I said at the beginning? We're trying to seek a balance, right? It's not, you can't just decide, oh, we want to go to Sarkatali because it's low risk. You have to show that the cost and the environmental footprint and the time, all of that is worth it. Is it worth all of those things in order to have a lower risk? So we were trying to balance these different objectives. So in addition to the risk, so we needed to decide, do we move the intake from here to here? We thought about the risk. What are other factors that you should consider before you decide whether or not to move the intake? Work with your groups and make a list of those other factors that would affect whether or not you move the intake. Go ahead. You have a couple minutes. The intake location. What are other things besides the risk?
I will own it to the foundation. I was trying to bail them out.
Right? If it's very, very expensive, then we couldn't do it. So you have to consider not just the risk, but also the cost. What else would you consider? This table, please.
Quantity of water.
The quantity of?
Water.
Oh, the quantity of water available to the intake. Yeah, good point. Excellent point. The whole point of the project is to bring water to the city. So if you move this so far away that there's not much water, there's no point in moving it. Great point. What else?
Geological setting as well.
The geological setting. So other types of issues, like you don't just have the risk related to landslides, you have the geological setting that affects the construction and the cost of construction and the ability to construct. Yeah.
Stability of the ground.
Stability of the ground under the structure, yes.
Orientation of the proposed location in the river.
Yes, the orientation, yeah, the relative orientation of the river to the location, yes. What else?
Proximity to tunnel.
The proximity to the tunnel, yes. You have to be in a place where the tunnel can come to in a short distance. The time, yes, the time it takes to construct. All good, 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 good. I'll move on. So what we did was we made a long list of the other factors and we kind of put them into groups. And those groups we put into different rows here. So let's just look at the rows with me. So the first was the risk of closure. So that's what I showed you with that simple matrix. That's one thing we considered. The next thing that we considered was cost. Of course, it was too expensive, we couldn't build it, so we had to consider it. The next we considered was timing. It's very important that this happens quickly. So something that takes a really long time, it's not possible. The next was ease of construction. So is the geological setting, is the distance close enough that we can actually build it easily and cost effectively? The next was operational reliability. Right? Because of the geologic setting, because of the access, because of the ability to arrive there, we needed to be sure that in the future there's options for fixing it if something goes wrong. We call that operational reliability. And then the last was environmental and social. So at some locations it's not possible to build because of the social and environmental constraints. So what we did, we used what we call multiple criteria decision analysis, where across the top here, these are the 4 locations. 1, 2, 3, 4. For each of these items, we basically ranked them. So for risk, for example, option A, at the existing intake, we said it's unacceptable risk. Let me just tell you, it's unacceptable risk. We decided the risk was too high because I described previously, we can't stabilize the landslide, so therefore the risk is too high for us to accept. So I'll just jump to the answer. We said this is no longer even an option. There's actually no point in looking at the other factors because the risk is too high, we won't look at it. So then really we were just comparing the other 3. So what we did is for these other 3, we basically just ranked them. So for cost, for example, we said, well, the one that's farthest away costs the most. The one that's closest costs the least. But these 2, because of complications with construction, although it's closer, it would be more complicated to construct. So in the end, the cost was about the same. So we said both have about a moderate cost. And then for timing, we said, well, because of those construction issues, both have about the similar timing. They both cost about the same amount, so we called both of them moderate. Ease of construction, well, this narrow gorge is very narrow. It's very difficult to get in there to construct. So we said that would be difficult. It's a narrow workspace. But the Strouth has very good access. It's very open, and it's very easy to construct there. Then for the operational reliability, again, it's related to the access. And then for the environment, they're about the same. So we went through and we described them using words first. After we did that, we came through and we assigned a score to it. So each category, we just ranked them relative to each other. So in this case, the highest score wins. If you have the highest score, you're the best. So for the cost, B, we decided it was the lowest cost option, so we gave it the highest score, right? So the highest score was actually to leave it at the existing intake. That's the lowest cost option, but I said it was already dead. So then the next lowest cost would be the next closest.
Alex, can you zoom in a bit on the table? Because I suspect it's very small for the people in the back. Well, that's complicated. Sorry. Maybe not possible.
I can't.
Okay.
But the point is that the way that we do this analysis is we just compare the different options, we assign a score to each of them, and then when you add the score, you find that this option C, it has the highest score, and because it has the highest score, it wins. That's why we chose that site. Now, there's no magic to the scoring. The point of it is really more a communication tool. It's so that we can explain to somebody else. When somebody says, hey, why did you choose this site and not the other site? Well, we say it's a complicated decision, right? We're trying to weigh many different factors. No site is perfect. One site is better in this factor, another site is better in this factor. So considering all of those factors, the best balance of managing the risk with managing all of these other factors was this C, and the score demonstrates that, and now we can explain to somebody all of the reasons why we accepted it. And we accepted this site because it's low risk. The cost and timing were moderate. It's not the best for cost and timing, but it's not the worst. It has very good access. That makes construction easy, and the good access also makes the operation easy and reliable. Because if a problem happens, you can arrive there to clean it out. And again, this access is actually not good, let me say, but it's good relative to the other sites. You're just comparing it to the other sites. And then lastly, the environment. So yes, there's an impact. It's not the best case, but it's not the worst. So it has a moderate impact. So basically, although this site is not really the best in anything, it's the best site because it's moderate in everything. It's not the worst in anything either. Does that make sense? So later, years from now, when you hear complaints about the new location not being the best for cost or the best for timing, now you understand, we recognize that. It's not the best, but it's the least worst. And that's why we chose it. Are there any questions about this method or about the decision? Okay. So the fourth decision was, what is the most reliable layout of the intake? So now we have chosen a new location. So how do we design the intake so that the water is always flowing? That was the next question. So now we've actually worked through this whole site-specific process, right? We started by identifying the risks. Then we talked about generally the risk reduction options. Then we used decision tools to help us pick the location. And now we're getting into more of the detailed design at that location. What exactly will it look like? The way to begin a design, the same way that you begin a risk assessment, is to define your objectives. So our objective, the big objective, was to have an intake that was reliable. And when I say reliable, I mean intake that always has water flowing to the site. So to add more specific to that, the objectives were, we want the water to always enter the intake even during low flow periods. Right? So in low flow, the river is actually very small. It's only about 2 or 3 cubic meters per second. And it's a little thread in this wide sediment plain. So we need the water to enter even in that condition. We also want the intake to operate every year during the monsoon. And during the monsoon, we have debris floods, probably every year. There's at least a small debris flood. And in many years, there's a large debris flood. But even during that condition, we want water to be passing into the intake. We also recognize that because of these debris floods, that we can have very large changes in the bed level. We can have deposition, we can have erosion, and so we estimated that the bed could be moving up and down by something like 20 meters. We said we still want water to enter even with those changes in the bed level. And another objective that we had to design from the beginning, and I think probably Emily mentioned this and I wasn't here for it, but when you do a design, you have to also design the maintenance that's required, and you have to also design the disaster response. That all happens during the design process. And we decided at the very beginning that it wasn't going to be reasonable to have no maintenance. It wasn't going to be reasonable to build something and just walk away from it. So we said, okay, one of our objectives is that we design something that allows that continuous maintenance will always be there. There's always going to be equipment that's needed to make sure that this structure is operating. And the reason is, you might say to me, well, most of our intakes, they don't need that. But what's different about this one is we have this large debris source that's causing debris floods to happen every year, constantly, constantly, constantly. And because of that, we need to have maintenance available. So I'll just describe to you now generally what the components of the intake are, just so you generally understand how it works. So here's the river. It's flowing from the top of the screen to the bottom of the screen. One thing that we did was we mapped the bedrock. So this is the red. And we said the bedrock is exposed in these areas. And bedrock was important to us because, remember, we have erosion and deposition happening with the debris floods. And if we're on bedrock, we know that the erosion will not be into the bedrock very deep. Not much. So we know at these locations we're more confident about what could happen to the bed. We know here that the bed is only rising. It can't go below. If we place the intake somewhere on soil, then we'd have to manage two issues. We'd have to manage erosion as well as deposition. So we chose bedrock, so we'd only have to manage the one issue. The way it works is the water flows along here, and we have what's called a side intake. So it's on the side of the river. The water flows, and a portion of it is diverted out of the side of the river into the intake. That intake looks like this tower here. So this image here is as if you were a piece of the river flowing down the stream into the page past the intake. So this face here would be this one along the river. Is that clear, what you're looking at? So you can see this little gray line maybe. In the back maybe you can't, but you can imagine that there's a gray line here. This was the bed level before the event. So we had this much erosion, more than 20 meters of erosion at this site. And that tells us that with time, because of debris flows and debris floods that are much smaller, that you could have the bed level that rises up to this location with time. So we designed an intake that allows for that aggradation to occur. And it's protected from erosion and degradation because it's placed on the rock. So basically what happens is the water enters the intake, it falls down the tower, and then it passes into the system. That system is a sediment management area. So this is a slow spot, so the river goes into like a pool. And when it goes in the pool, it moves very slowly in the sand and the gravel and the silt. It falls out of the water. Then there's mechanisms that flush that sand and sediment back into the river. This is called the sluice outlet. And then the clear water continues downstream. Now a key issue is that this sluice outlet, it has to be above the river level. So remember that we have this aggradation or deposition that can happen in the river. If that happens here, it'll bury the outlet. And then we have the same problem that we have with the existing intake, which is that the sediment that comes in, it can't get out. So it's actually this outlet that becomes very critical. The outlet must be high enough above the river that it can flush the sediment. And that becomes a very important geometric constraint, that you have to have a gradient of the river that's steep enough that this outlet is high enough above the river that it can still outlet. So that really controlled some of the location selection. That's how it works. Any questions about the way it works? No? Okay. Yes?
Do you mean at some points what would the intake structure or the existing intake structure?
Good point.
And we didn't recommend the same cross intake structure. I think that's better to understand.
That's a great point. I'll just use my hands. I could draw it, but I'll use my hands. Is that okay? Or should I draw it?
Maybe we can use that.
Hold on, I'll do it. We have time. So if you go over, you can blame Kashal, right? Not me.
Sure.
Blame him. Okay. Look more like this. So first I'll draw it in plan view, like looking from above. So imagine you have the river like this. It kind of goes around the corner like this. The previous intake had across it a weir. On the side of that weir, this is where the water entered into the intake. Yeah? And from there, it went down, sediment management, and now this way into the tunnels. If you were to look at this structure if you were to be this arrow that's looking downstream at the structure, it would look like this. That, and maybe the bed is down here like this. Does that make sense? So the water is flowing kind of directly into the intake on the side, and there's sort of a dam. This is the weir. This dam controls the level of the water, so it creates a pond. Right? So we have this head pond. Yeah. And so the water then flows directly in. The concern with this, and then this portion of the water here is flowing over the weir. And now if we look at a section, let's say right here, the way it works is you would have so now you have the water at the bottom over here, but up at the intake, the water's up in this level, like up in here. Right, so over here you have the water up high, and here you have the water down low, and then you can have the sediment that flushes out back into the river. Does that make sense? Yeah? And what makes this vulnerable is that this height here is about 4 meters. And so when you have sediment that comes in, the sediment fills this pool and fills the entire intake. And the sediment, the boulders and the gravel, they flow into the intake and they're able to block the intake. The shop must be happy with it. He's not even listening. Instead of being what we call a front intake where the water would flow straight into it, now the water is being taken off at the side. And we have all of these bars. It's like a grill or like a mesh of steel that allows the boulders to hit it without the boulders entering into this tower. That was the other thing that is different. Any questions about the differences? No? Okay. Let me say one other thing. That's that we considered other types of intakes. The one type that I just described for the previous intake, that was a frontal intake, or maybe it's a side intake, but we don't have to get into this debate of semantics there. There's this design, which is really a novel design. There isn't much experience with it anywhere, actually. Another design that was considered and may actually become the design in the end is called a Tyrolean weir, or a bottom intake. And the way that works, you have a structure where this goes across the river, all the way across, and it has a mesh, a steel mesh in it, so that the sediment passes over and the water falls into it. And then it goes off to the side and into the system. Now, this location would be a very poor location for that Tyrolean weir because the sediment would bury it. But there is a potential to put that type of system here just downstream because it's very narrow and you always have erosion there. So in the next stage of the design, in the detailed design, there will be a more detailed comparison between these two types of intake, whether you do a bottom intake or a side intake. But as that assessment is done, the key will be managing the vulnerability to it being destroyed or blocked. Right? So I'm just trying to illustrate or make that point because you might hear 5 years from now that what was selected in the end is a bit different from this. But if that's the case, it's because that other option manages these risks better than this option. Right? And it's always going to be balancing the different issues. Okay, I'll go for another few minutes, 5-10 minutes, yeah? All right, so when you're designing something, your objectives, which I did, you've probably all forgotten now, but remember I talked about our objectives: water entering during low flow, entering during monsoon. We allow for the big change in bed level. So we define design scenarios. These are really helpful for us to organize all of our design tasks. So we have our low flow scenario. We say we want the design to work when the water is really low, less than 1 meter deep and 3 cubic meters per second. We want it to work during a normal flood that happens every year. We also have these debris floods, similar to what happened before. And then we have something like an extreme debris flood that's really big. So we need to think about how these different events interact with our structure. And so for each of those events, we define what we call performance levels. So this describes like how we want a component of the design to function. So the first one, continuous operation. This one is, we want it to function without any damage. We want it to operate continuously. We want it to just keep working even not knowing that the event happened. That would be that level of performance. That's the highest level of performance. The lowest level of performance is called recoverable loss. So we say, all right, this thing, we'll allow that something will damage it, it may break it, but we want to be able to rebuild it afterwards. That's the worst performance level. And then there's an intermediate one that says, well, we'll allow it to be damaged, but it needs to be recoverable. And then what we do is we make a list of every component of the design. So here I'm showing you 2 of them, but there might be 15 of them in the end. And we basically just match what is the design scenario, how does that relate to the performance that we want for each of those components. So for the very critical components like the tower and the sediment flushing, these things, they cannot fail, because if they fail, the whole system is broken. So for that case, we want it every year to have this continuous operation. It means it happens, we don't even notice it for the common floods. But we'll allow for these critical elements that if you have a very rare debris flood, a very extreme event that happens very rarely, we'll allow it to be damaged as long as it can be recoverable. That makes sense? Other components that are less critical, like if there's a training berm in the river that diverts the flow to the outlet, that could be repaired very quickly afterwards. There we do it differently. We say we want the common low flow to always operate, continuously operate, because we want to divert those low flows into the outlet. But we will allow that the entire river training will be destroyed by debris floods. If you say, it's not cost effective, it's too expensive to build river training that won't be damaged, so we can allow it to be completely destroyed, and we can rebuild it later. Right? So that's a cost trade-off that we're trading off the operations costs. So we're saying there will be higher operations costs, but less capital costs. This is kind of the trade-off decision that we're making. And we make that decision by matching these performance levels with our design scenarios. Once we do that to set the objectives, then we optimize the design of the components. So this is actually doing the design, doing the calculations. And as I said, when we're designing the individual items, we're always comparing the capital cost to the operations and maintenance cost. Right? So you always have this decision to make. Whether do you want to spend more money now to build something that's stronger, that doesn't need maintenance? That'd be this first option. Or do you want to build something that's weaker, but needs more maintenance? So in the end, the strong option, maybe it costs less over the 50-year design life. But, maybe depending on the funding, it's okay to pay more in the long term because this other option costs less in the short term. So you need to make this balance, and you need to do it with your eyes open. You need to do this intentionally and discuss it and do it, consider this as you do the design. So that's actually it. That's my key, that's the end of the presentation. Let me summarize the key messages quickly. Number 1, I hope you learned. I hope that you're sick of hearing this, that it's not always possible to reduce the hazards. It's not possible. And when you can't reduce the hazards, you need to reduce risk by reducing the vulnerability and the exposure. The next point is when you have a very big problem, it can really help to break it into small problems. That's the way to actually make progress. And then the last is that you should define the design objectives that lead to reliability. You can't just say, we want it to be reliable. You have to break that also into smaller components. So that's the presentation. I'm a bit over time. We have an option to do group exercises related to this, but we can decide later if we'll do those or not. I don't know. Okay. Thank you.